we will start module 12, and in module 12 the topic will be complex variables, functions of complex variables, differentiation and integrations of these functions. Now there are a lot of interesting mathematical techniques that you will see, and one of the most interesting ones is what is called the residue theorem, okay, and we will build up to that. And this is actually a very powerful technique of evaluating various integrals, especially you can do integrals of real functions using complex variables. Okay. So that will be one of the very powerful techniques that we will learn. Now one of the first questions when you think of complex variables is why should we have complex variables? I mean, the real world is full of real quantities. Why should we have complex variables? Now there is a very intuitive way to understand this, and that is the following, that yes, you do not need complex variables, you can work entirely with real variables, but there are certain quantities. For example, if you take a wave, okay, that has both an amplitude and a phase, and if you have both an amplitude and a phase, then you can use two variables to describe it, or you can combine those two variables into a complex variable. Okay. So there are certain quantities which have this which have within them two variables, and therefore to describe waves it is convenient to use complex variables. So this is just one example, but the point is complex variables are useful, okay, and are very convenient methods, are very convenient for describing the real world where actually quantities are real. Okay, and we will see some of the aspects of this during this module. Okay. So I will start with lecture 1, and in the first lecture I will be talking about very basics of complex variables, and show some functions of complex variables, and already when you start writing functions of complex variables, we will immediately see the idea of branch cuts. Okay. So let us start. Okay. So a complex variable is a complex number is a ordered pair of real numbers. Okay. So you can have something like A, B, where A, B are real numbers. Okay. And then so this is the basic definition of a complex number. Okay. And this is conveniently written as, it is written as C equal to A plus I B, where I is used to, I is taken as square root of -1. Okay. This is used to define multiplication of complex numbers. Okay. So for example, if you have various operations, if you have addition A1 B1 plus A2 B2 is equal to A1 plus A2 B1 plus B2. So it is just like vector addition. Okay. Now now you go to multiplication. So if you have A1 B1 multiplied by A2 B2, okay. Now this works out to the following: A1 A2 minus B1 B2 A1 B2 plus B1 A2. So this is the definition of the multiplication, and you can verify this using this form of complex numbers. Okay. So these are the basic rules, and with this you can do everything that is involved in complex numbers. Okay. Now there is a very now a complex variable z is a combination of two real variables, we will call it x and y, or equivalently we will write it as x plus iy. Okay, so x and y are real variables. Okay, so now since x and y are real variables, okay, so minus infinity less than x less than infinity, minus infinity less than y less than infinity, okay, this is the range of real variables. Okay. Now if you have two variables x and y, okay, then you can pictorially describe the space occupied by both those variables in terms of a plane. So the complex plane, this is basically the xy plane. So you have the y plane and you have the x plane. Okay. So this is the complex plane, and if you take any point x y, it has a real part, this is the real part x, this is the imaginary part y. So you have this point is x plus iy, and this is x is the real part, this is called the imaginary part. So any complex number has both a real and an imaginary part. So now what you will see is that along this line, this is a real line. Okay, in the sense if this variable lies along the x line, then it will be only real. So along this line, if your complex variable lies along this line, that means the y component is 0, so it is purely real. On the other hand, if it lies along this line, then it will be purely imaginary, because the real part is 0, so it will be purely imaginary. So this is the imaginary line. Okay. So these are two properties of complex numbers. So suppose your number is purely imaginary, it does not have any real parts, that means the x is equal to 0, then it will lie along this line. Similarly, if y equal to 0, it will lie along this line. But in general, if it has both the real and imaginary parts, it will lie somewhere else. Okay, and both the real and imaginary parts can be positive or negative. Okay, this point, if you think of this like Cartesian coordinates, you can immediately think of polar coordinates. Okay, so can we have something like polar coordinates? Okay, and the answer is yes, you can have polar coordinates. Okay. Now here you define, you write your, so what is done is you write z equal to x plus iy equal to r e to the I theta. Okay. So in other words, this is equal to, now e to the I theta I can write as cosine theta plus I r sin theta. Okay. So I have r cosine theta plus I sin theta, so I multiply it by r and I get this. Okay. Now what you see is that this implies that x equal to r cos theta, y equal to r sin theta, just like usual polar coordinates. Okay. So that means I can write, that means r will be given by this. Okay. So this implies r is equal to x square plus y square. okay, and it implies theta or equal to tan inverse y by x, okay, just like usual. So, this is my r, this is my theta. Okay. So, you can use polar coordinates, okay, and you can write your complex variable as r e to the I theta. Okay. So, just to summarize, I can write my complex variable as x plus I y, or I can equivalently write it as r e to the I theta. Okay. And both these are valid descriptions of the complex variable. Okay. And it's once we you can use either of these descriptions based on what is convenient, okay, and we will see some examples of that. All right. Now, one more thing I want to mention right here when we are talking about complex variables. Okay. So, we can define, corresponding to a complex variables, there is a concept of a complex conjugate. So, z star is equal to, this is given by x minus I y, okay, and in the complex plane you can see what happens. So, if you have a complex variable x y, then this point where you have x minus y, this is a complex conjugate, and you can see that the angle is minus theta. Okay. So, the angle is measured always in the counterclockwise direction starting from the x axis. So, this is minus theta. Okay. So, this is equivalent to r e to the minus I theta, okay, and what you can see is that z star z equal to z star is equal to r square is equal to x square plus y square. Okay. So, now what is done is that analogous with 2 dimensional vectors, okay, r is identified as the amplitude of the vector or the length of the vector. So, r implies r equal to length of vector, or it is equivalently called modulus of z, or it is equivalently called absolute value of z. Okay. So, these are the, you can immediately identify r with this. Okay. So, if you have a complex variable x plus I y, you can immediately identify that its absolute value is square root of x square plus y square. Okay. So, this is basics about complex variables. Now, let us go to functions of a complex variable. Okay. So, what I have tried to say is just I have just tried to show the complex variables, and you can see that complex variables naturally fall into the complex plane, and you can describe them either in terms of x y coordinates, that which is Cartesian like coordinates, or in terms of polar coordinates. Keep in mind that the absolute value of the complex variable is just square root of x square plus y square. Okay. So, now let us go to functions of a complex variables. So, just as you can have f of x, okay, this is function of a real variable, you can have f of z, and this is function of a complex variable. Okay. And now we can say that in general, if in general f of z is now z is an ordered pair of 2 real numbers. So, this is like a function of x y. Okay. Now, in general f can be complex. So, f can be written as 2 functions, Okay. So this is a real function, this is also a real function. Okay. So u of x y is a function of x y which is a real function of x y. Similarly, v of x y is a real function of x y, I is the square root of minus 1. So I can write the function as having a real and an imaginary part. Okay. So this is so u real part of f of x y and v of x y is the imaginary part of f of x y. Okay. So this is what you can say about the functions of a real variable or functions of a complex variable. Now, there is something very interesting that happens with complex variables. Okay. This has to do with the property, with the following property. So, note, so z is equivalent to r e to the I theta, okay, which now we have e to the I theta is equal to e to the I okay. So, first I will write it as cosine theta plus I sin theta. Now, cosine and sine are periodic functions, okay. So, and their period is 2 pi. So, cosine repeats with period 2 pi, similarly sine repeats with period 2 pi. So, I can write this as e to the I theta plus 2 pi, and I can multiply it by 2 pi multiplied by any integer, positive or negative integer. Okay. So, this is a property of this of e to the I theta, okay. And what we will see is that this introduces some very interesting properties when we are dealing with complex functions. So let us we will see how this affects the description of complex function. First let us look at some simple functions. So suppose you have f of x y, or let us take suppose you had f of x equal to 1 plus x square plus 2 x, okay. You can have a corresponding similarly we can have f of z is equal to 1 plus z square plus 2 z. You can have f of z in the same way, okay. Now, so z square is defined just like as we saw before. So now let's try to write this. So if we write f of z is equal to 1 plus or is equal to 1 plus, now z I will write as x plus I y square to x plus I y, okay. Now, I will write this as 1 plus x plus I y square is x square, then you have I y square, I square is minus 1. So, it will give you minus y square, okay, plus you have x I y and I y x. So, you have 2 I y x plus 2 x plus 2 I y. So, I can write this as 1 plus x square minus y square plus 2 x plus I 2 x y plus 2 y. So my u of x y is equal to 1 plus x square minus y square plus 2 x, and v of x y is equal to 2 x y plus 2 y. Okay, this is what corresponds to this function. Now if you want to write this in polar coordinates, so suppose I take f of z is equal to 1 plus z square plus 2 z, this is equal to 1 plus r square e to the I theta, it will become e to the 2 I theta plus 2 r e to the I theta. Okay. Now, now what we can see is that we cannot directly write this in polar coordinates. So, we can go to this description, we can go to writing it in terms of u and v, and then writing it in terms of polar coordinates. Okay. So, it is not straightforward to write this whole thing in terms of polar coordinates. So, what we do is we go back to u and v, okay, and then write it. So, we write f of z. Okay. So, I can write this as u of x y, v of x y, and I can equivalently write this as u r of r theta, v r of r theta, v theta of r theta. Okay. So, u is a function of, or I will write this in the following way. So, I will write this as square root of u square plus v square e to the I phi, where phi is equal to tan inverse v by u. So, I can write this also in polar coordinates. Okay. Now, what you notice is that f of z is equal to 1 plus z square plus 2 z. Okay. So, along real line that is z equal to x, f of z is equal to 1 plus x square plus 2 x. Okay. So, in some sense what we will say is that this function f of z is a complex function. The complex function somehow that is I will say it slightly casually right now, that is related to real function okay. So, what I mean is you have this real function 1 plus x square plus 2 x, okay, and this is a complex function, okay, which along the real line has this value, but it extends the real function to the complex plane. Okay. So, that is what I want to make this point, and formally this is known as something called analytic continuation. Okay. So, you are extending a function of a real variable to the complex plane. Okay. Now let us look at a couple of other examples of interesting complex functions. So, suppose you have f of x is equal to square root of x. Okay. Now, the extension the corresponding complex function f of z is equal to z raised to half. Now, z raised to half I can write it as x plus I y raised to half, okay. And this does not seem very intuitive, but let me write it slightly differently. Okay. I will write this as r e to the I theta raised to half, and this is equal to r raised to half e to the I theta by 2. Okay. So, now what does this look like? So, if this was my point which was given by x y or theta, okay, then the square root will have angle theta by 2 and it will have length of r raised to half square root of r. Okay, so this is what your square root of, so this point is square root of z. Okay, now this is not the whole story. This is not the whole story. Okay, but you notice that by using the polar coordinates, we were easily able to take the square root. Okay. Now what is, why did I say this is not the whole story? Okay, the reason is the following, that usually we can have for a real number. Okay, so you can have square root of x square equal to plus minus x. Okay, it can be both positive and negative. Okay, so when you take a square root, okay, then you can have both a positive square root and a negative square root. Okay, now usually when you take square root of r e to the I theta, okay, now this we choose to be either positive or negative. This we choose to be positive because this is the amplitude. Okay, so the leading power is the amplitude of this wave, that can be positive or negative. no, that is chosen to be positive, but this can be taken as negative. Okay. Now what does that mean? So you can have f of z equal to z raised to half as r raised to half e to the I theta by 2 or r raised to half, or I will write it as minus 1 into e to the I theta by 2. Okay. Now where does this minus 1 come from? So let us write, now we note that minus 1 is equal to e to the I pi. Okay. So e to the I pi is equal to e to the I 3 pi is equal to e to the I 5 pi and so on, is equal to e to the minus I pi is equal to, so in general equal to e to the I 2n plus 1 pi, where n equal to 0, 1, 2 or 0 plus minus 1. Okay, so it is an odd multiple of pi. So for any odd multiple of pi, e to the I pi is equal to minus 1. Okay, so now just let us look at this. So what this means is that I can write this as, so f of z is equal to r raised to half e to the I, let me look at e to the I pi first, e to the I pi plus I theta by 2, this is r raised to half e to the I theta plus 2 pi by 2. Okay. So now what we see is that there are two possibilities. You can have f of z is equal to e raised to I theta by 2 or f of z is equal to r raised to half e to the I theta plus 2 pi by 2, and both these give different results. So both these will give you different results. Okay. So these two results will actually be different. Okay. In one case you will get something like this, in the other case you will get something like this, exactly negative of that. Okay. So, in other words you have the same r, but you have theta increased by this angle is theta by 2 plus pi. Okay. So, basically when you take a square root, you can have two possibilities, you can either have this possibility or this possibility. Okay. And this is a complication that comes, and so we say that square root function has two what, and the term used is branches. Okay. So, the function has two branches, okay, and the two branches, okay, the origin of having the two branches can be understood in terms of this equality, that e to the I pi is same as e to the I theta plus 2 pi m. Okay. Now, whenever you take an odd integer multiple and then you take the square root, okay, then you will get negative of that. See notice that notice that e to the I pi, okay, is same as e to the I 3 pi, e to the I 5 pi and so on. Similarly, e to the 0 is same as e to the 2 pi I, 4 pi I, 6 pi I and so on. Okay. When you take the square root, okay, then suddenly the two values become different. Okay. So, when you take the square root with if you have 2 pi I, okay, then the square root will give you a positive square root. If you have a 2n plus 1 pi I, then you will get a negative square root. The square root will give you a negative number. Okay. So, we will just summarize this point that that if you take square root function, okay, then there are two branches, okay, there are two branches to the square root function. In one branch your theta will be between 0 and pi by 2, in the other branch your theta will be between it will be between 0 and pi in the first branch. Okay. So, that will be in the upper half plane, the other branch your theta will be in the negative half plane. Okay. So, what we say is that there are these two branches of the square root function, okay, and they are cut, there is a branch cut that divides these two functions. Okay. So, I will show it as this is how I will show the branch cut. Okay. So, the branch cut actually divides this function, this is called the branch cut. So, what this means is that as you cross this line, okay, so your function will smoothly vary. So, r raised to half e to the I theta by 2. Okay. So, this will actually be continuous all the way up to here, but when you cross, so it will be continuous and then it will take there will be a jump when you cross this line. Okay. So, if you go from here to here, if you go from here to here, okay, and you go back, so all this is continuous. Okay. And there is a discontinuity. So, this is a discontinuity in f, in the function f. Okay. So what it means is that if I look at the value of the function just below this line and if I look at the value of the function just above this line, okay, that means if I look for if I then what I will see is that there will be a jump in the function. Okay. So that is the meaning of this. So just for example, let us take a point where example r equal to 1, okay, and so when theta equal to 0 plus, okay, that is just greater than 0, then f is equal to 1, okay, theta equal to 0 minus, okay, then then f is equal to minus 1. Okay. So the function goes from minus 1 to 1 across this point. Okay. This is for the particular case when r was equal to 1. Okay. But any square root function will show a jump across this point. Okay. So the square root function will always show this jump across this line. Now notice that on the other side you don't have a jump. Okay. So what we say is that square root of z has 2 branches, okay, and branch cut along positive real axis. Okay. So this is what we see from here. Now you know, things can become more complicated. Okay. So let us take the example of log. What about log z? Okay. Now what I want to emphasize, one more thing I want to emphasize is that if we use z equal to r e to the I theta plus 2 n pi, okay. If we use this, then this implies z raised to half is equal to r e to the I r raised to half e to the I theta by 2 times e to the I n pi. Okay. And what these two branches corresponding to, they correspond to n being odd or n being even. If n is odd, okay, then all the terms with n odd will correspond to the negative branch, the branch where this is minus 1. Okay. So n can be odd or even. So this is equal to r raised to half e to the I theta by 2 if n even equal to r raised to half minus r raised to half e to the I theta by 2 if n odd. Okay. So these are the various possibilities that you can have. Okay. Now what about log z? Okay, and this is something that will get really interesting. So we do the same thing, we take log z as log z equal to log of r e to the I, and now we will write it as theta plus 2 n pi. Okay. This we use a property of logarithm, you write it as log of r plus, now log of e to the I theta plus 2 n pi will give me I times theta plus 2 n pi. So now this is interesting. So n is equal to 0 plus minus 1 plus minus 2 plus minus 3 etc. So now what you see is that there are many branches. Okay, this is a, so for each value, whatever value of n you will take, you will get a different branch, because the logarithm will have a different number, will have a different imaginary term. okay, and each of these functions are a different functions, okay. And in such a case you say that log z equal to so if we write so you can have either log z equal to log r plus I theta, it can be equal to log r plus I theta plus 2 pi plus 4 pi and so on, can have many branches, okay. And this branch where you take n equal to 0 is called the principal branch of log z, okay. So this is something that you have to be careful whenever you see functions of a complex variable, okay. You can also ask where the branch cuts are, okay. So what is the place where all these branches are they cross, okay, and that also you can see, you can easily identify the branch cuts, okay. Now okay, so we will I won't discuss more about this, okay, but basically what I want to say is that depending on your choice of theta, okay, your branches can have different values, okay. Now notice this is actually changing the value of the logarithm, okay. You should be very careful in identifying that the actual value is changing, the value of the function is changing in each branch, okay. So in the first branch it was just the imaginary part was just theta, in the second branch the imaginary part is theta plus 2 pi, okay, and you can have many more branches like that. So I'll conclude this lecture here, okay. What I have tried to show is that even your simple idea of functions, okay, becomes more complicated when you are dealing with complex numbers, okay. But we have seen that you can talk about functions, okay. Now in the next lecture I will try to formalize this a bit more, do the ideas of continuity, okay, and differentiability of functions, okay. So I will conclude this lecture here, and for now thank you.